Math 3C Week 9. As usual, reading quizzes due Thursday, graded assignments due Friday. Nicely this week, no chapter exam. Sections this week are 4.5, 4.6, 4.7. Here are your checkpoints. First up, the chain rule. In the chain rule, we are presented with a function w depending on x's, y's, and z's, yet we're being asked to find a full derivative dw dt. Not a partial, but a full derivative. We're going to employ a tree diagram. We make a little dot to represent w. And then we look at all of the variables that w takes as input, and for each variable, we draw a branch. At the end of the branch, we make a dot, a node, and then we put a label on that dot. We continue reading the problem, and we see that each of those dots is going to be a function of a single variable t. So from each dot, we draw just a single branch, which ends at a node t. Then, to employ the chain rule, we simply read down the branch until we get to the final node. And we see that we have 3 branches to read down to, each terminating in t. Hence, to find this quantity dw dt is going to produce 3 terms. Then each term is a product, and each factor represents one branch of the 3. Okay, so this is partial w, partial x, and that's the top portion of the branch. Going from w, how does it change? How does w change the outputs as you vary input x's? However, the x's can change in value by changing an input t. Yet, in contrast, w partially depends on x. In contrast, x fully depends on t. Hence, this branch here is labeled with a partial derivative, and this branch here is labeled with a full derivative. And so you need to be careful when you write that out. And then you repeat for each variable, x, y, and then z, where you have a partial being multiplied by a full. Next, you simply look at all of the factors. This is a partial of w with respect to x. Here is w, x, y, cosine z, x, y, cosine z, then partial with respect to x. You know that the y and the z are held constant, and the derivative of x is simply 1, so that partial is y cosine z. You do the same thing, look at the definition of x depending on t, plug in for x, get d by dt of t, and produce 1. Repeat. After that's done, you then want to come up with an expression for the rate of change of w with respect to single variable t. So you now, at this stage, want to go from x's, y's, and z's and translate them into just t's. So if we look at y is t squared, we swap out y for t squared. To find cosine of z, z is defined as the arc sine of t. So we can make a nice little right triangle. Arc sine produces angles as output, so I have an angle z. Sine is defined as the opposite over the hypotenuse, so we get t1. And then using the Pythagorean theorem, we can come up with the adjacent side to z, and that is enough to help us find cosine of z. Continue plugging in, and then combine like terms, and all good to go. Nice. So that was 4.5. 4.6 is on this notion of a directional derivative and the gradient. The notion of the gradient is here denoted with this upside down triangle. That upside down triangle is read grad for short, or the gradient of f, grad f, or the gradient of f. In this particular definition, we're taking f to be a function depending on x's and y's, so that this f is scalar valued, but the gradient of f is going to be a vector valued function. And then a vector has components, plural. The number of components that it will have will correspond exactly with the number of inputs that the original function has. In other words, f takes inputs 1, 2, x and y, and hence the gradient has 1, 2 components. All right, so that's the definition of a gradient. Here is a nice property of the gradient. The properties are listed here in this theorem. I'm going to refer to the picture to explain. Here we have a picture in 3 space, x, y, and z. And then we have a nice surface, a paraboloid. And you want to look at this as a bowl. And then you want to place yourself in that bowl. And if you were to follow this arrow, that you would be exiting the bowl in the most expeditious way. If you follow the blue arrow, then you're going down deep into the bowl as fast as you can. So this direction is to exit. That means to go along the surface and rise on the surface as fast as you can. That's going to be a maximum rate of change. In contrast, the blue arrow is giving the direction in which you can stay on the surface and yet drop z's as fast as possible. Okay, so that's looking up here in 3 space. But the interpretation is going to occur on the inputs. The inputs of z's are given by x's and y's. So we need to look down there, and we have this nice level portion where the z's are constant, and that corresponds with these inputs, x and y. And then you have the blue arrow corresponding with this blue vector down here, likewise with orange. The direction of greatest increase, meaning that if you follow these inputs, then your output, your height on the bowl is going to remain the same. So you need to go normal to that direction. This is called a level curve, recall. You want to go normal to that direction, and in one way, you're exiting the bowl, that's greatest increase, and in exactly the opposite direction, negative grad f, is the greatest decrease. So the whole point here is that the direction that you increase the most and decrease the most is given by the gradient of the function that you're graphing. And that positive grad f is the direction increasing, negative grad f is the direction to decrease. Okay, so that's just the general gist. I did not state things technically. For that, you want to go and read the definition, the theorem closely. All right, so there's properties of the gradient, and then there is a nice usefulness for the gradient. And you can use it to find the rate of change in any direction that you like. So here's a problem 284 where a particular function is given to us. It's a nice polynomial in x's and y's. And then we want to consider this function at this particular point P. And then imagine that we're going to take inputs which vary away from P out over towards Q. And then in doing that, at this point P, how quickly will the outputs of F change? That notion is captured in the idea of a directional derivative. And what I've done is I've broken up the problem into 3 different steps. The first part is to find the direction. Second part is to compute the gradient at that point of interest. And then the third part is to compute a dot product. So let's take a look. The direction that we want to go is from P over to Q, so that's PQ vec. That gives us V vec. The important thing to remember is that you need a direction only, which means that you don't care about the magnitude of V vec. You want that magnitude to be of unit magnitude. Hence, you normalize that direction. When you take 4 and you subtract 1, that gives you 3. You take 5, subtract 1, that gives you 4. So V vec is 3, 4. Think of a right triangle, 3, 4, then the hypotenuse would be 5. That's just the Pythagorean theorem. Hence, the magnitude of V vec is 5. Okay, so now we have our unit direction that we wish to consider. To come up with the directional derivative, we simply need to take that direction, u vec, and dot it with the gradient evaluated at this point. To find the gradient, we first want to take partials of our function in the direction x, in the direction y, so that's f sub x, f sub y. The f is a very nice function. It's a polynomial, x squared, 3y squared. The second term, 3y squared, has nothing in x, therefore it's a constant in x, and therefore it will not change as you change x's, so that goes to 0. And the derivative, the straight derivative, the normal derivative, the 3a derivative of x squared is just 2x. So likewise, f sub y gives you 3 times the derivative of y squared, 3 2y. Take each of those pieces and plug in, and you come up with the gradient vector. Then look at the p. P has x equal 1, also y equal 1, so you plug in. X equals 1, you plug in. Y equals 1, and you get grad f at p as 2, 6. The directional derivative is then just simply the dot product of this vector and this vector, which is done here, and you come up with 6. All right, last section, 4.7. Mins and maxes is something that you have used calculus, first semester calculus, to find. And likewise, now that we're dealing with functions, scalar valued functions, but depending on more than one variable, we'd like to do the same thing here in 3C. Again, recalling back from first semester calculus, you had the notion of critical points in first semester calculus that either the derivative is 0 or the derivative does not exist. Same notion is going to hold when you have an f depending on more than one variable, except that you're going to state this in terms of partial derivatives rather than full derivatives. So f prime being 0 is now stated as both f sub x and f sub y are 0, that both partial derivatives are 0. If you can find such a point x naught y naught, then that point x naught y naught is a critical point for your function f. Alternatively, if either of the partials does not exist at your x naught y naught, then you have successfully found a critical point. Okay, so the usefulness of critical points is that they are candidate extreme values. And here we have an example problem that I'd like to look at, 352. So 352 is providing you with a constraint that you want a volume of 4 cubic feet. And you would like to come up with a box which minimizes the amount of cardboard. So I've restated that we want to optimize the usage of cardboard. So here is the surface area of that cardboard. And we have the constraint that the volume must be 4 cubic units. So if we let x be the base, y be the width, z be the height, then this would be the surface area, and then this is the volume. All right. Solution. Well, It'd be nice if we can reduce the number of unknowns in the problem, and that is how we're going to use the constraint. We're going to take the constraint and plug it into the function that we're trying to optimize, and the way that we'll do that is we'll solve for z as 4 over xy. We'll then plug that into our function f. That's going to eliminate out the z's and come up with f depending only on x's and y's. And that's done here. Now that we have f just depending on two variables, we'll go ahead and we'll take a partial of f with respect to x and y. We'll then require that those partials are 0, a la the critical points method. And then notice that we would also get a critical point at the origin, but that would require that the box is not going to exist, so we can eliminate those points, the origin. Playing around with some algebra, we'll come up with x equals y is equal to 2. Taking this information, plugging into this from the constraint, the formula for z, we'll come up with z equals 1. And then we found that the height of the box should be 1, and then the base of the box will be 2 by 2. So here, this work has just found the critical point. For your assignment, you're going to want to write this up in full. So you want to figure out how can you verify that indeed this critical point does lead to a optimization of surface area. Okay, and then the last thing that I want to do here in 4.7 is make a comment that, again, from first semester calculus, there's the notion of an extreme value theorem. You have one again in 3C. It's nearly identical. Immediately after stating EVT, the book provides you with a second theorem on how to apply EVT, and the application is, I'm sounding like a broken record, nearly identical to what you do in first semester calculus. In first semester calculus, you need to have a portion of the line which is finite, and then you would find a critical point on the interior. And then after you're done, you would make sure to check the endpoints. And then of those two, either on the endpoint or on the inside, you would take the largest and smallest and come up with the absolute min and absolute max. Same notion happens here, that you want to look in all of the domain, but then again you want to look on the boundary of that domain. Now this can be somewhat tedious. To see how tedious it is, I invite you to read, strongly encourage you to read example 4.40, where they're looking for the absolute min and max of this function, a nice function, on a nice rectangle. X is from 0 to 4, y is from 0 to 2. So if we draw out that rectangle, we can see that we're going to have to consider first critical points on all of D, and then the boundary of D, second, has, oh my gosh, 4 pieces to it. Hence, you're going to have to do 4 more calculations, which are 4 applications of EVT on what are going to turn out to be line integrals.